So parts per million percentages are useful, but what's most useful to a chemist is a concentration known as molarity, and this has to do with amounts in moles. So molarity, which is abbreviated with a capital M, is the number of moles of solute per liter of solution. So summarized here. The molarity of a solution is the amount of solute in moles divided by the volume of the solution in liters. And that's the whole solution, not just the solvent. It has to be moles per liter. You can't use other units here. So here's an illustration of how you might make a 1 molar sodium chloride solution. 1 molar means the concentration is has a molarity of 1 mole per liter. So one way to make this solution, you'd use a flask. These are called volumetric flasks, and they're calibrated to give a precise volume. So you can have a 1 liter flask here. It's got a mark on the neck that tells us the volume is 1 liter. So we would weigh out 1 mole of sodium chloride and add that to the flask. Then we would add water. You don't want to fill it all the way up at first. You want to fill it partially and mix it up real well, get the solid to dissolve, and then finish filling with the liquid, the water, all the way up to the neck. We have the volume of the entire solution is 1 liter. The volume of water is not 1 liter, right? Because adding the salt adds some volume, and it's not a predictable amount. But you could try this at home. Fill a glass all the way to the very tippy top with water, and then put a teaspoon of salt in it. What's going to happen? The water's going to spill over the edge, right? Because the salt displaces some of the water. That's why you always make sure it's dissolved before you fill it up to the volume. Then you would have to invert this and mix it really well. So calculate the molarity of a solution made by putting 55.8 grams of sodium nitrate into a beaker and diluting to 2.5 liters. So molarity. You see that, calculate the molarity. We need the equation. So molarity equals moles of solute. So moles, here the solute is the sodium nitrate, divided by the liters of solution. Did they give us either of those numbers? Yeah, they gave us 2.5 liters. So it was diluted to 2.5 liters. That tells us the volume of the whole solution is 2.5 liters. So that equals liters of solution. Sodium nitrate is the solute, but they didn't give us moles. They gave us a mass in grams. But we know what to do with that. We can convert grams to moles using the molar mass. So here's our molarity. We're going to weight on the numerator there, but the denominator is going to be 2.50 liters. And then we have to convert this 55 grams into moles. So we'll have grams in the bottom and moles on the top, so those units cancel out. We need the molar mass of sodium nitrate. So there's 1 mole of sodium in there, that's 22.99 grams, and there's 1 mole of nitrogen, which is 14.01 grams, and there are 3 moles of oxygen. So we add all those up. And we get 85. It's like when you go to the grocery store and it comes out to be like $100 even. You're like, couldn't do that if I tried. 85, does that an exact number? Does it have 2 significant figures? What do we do with that? How many significant figures should it have? 2 decimal places. Yeah. It doesn't have any decimal places, though. What do? Well, your calculator doesn't understand what significant figures are. It just does the math. And if it's got 0.0000, it doesn't bother to show you that because it doesn't understand that that might be important. We need those 2 decimal places because they are significant figures. It's 0.00. And sometimes we have to add that in. Grams of this substance per mole. So then here, the 85 is going to go in the denominator, and 1 mole in the numerator. 1 mole of sodium nitrate weighs 85 grams, 85.00. So we have 55.8 divided by 85. And this is should have 3 significant figures, so 0.656. Write down 2 extras, and that's moles of sodium nitrate. If that was the answer I was looking for, then I would round that and report it with 3 significant figures. But that's not my final answer. I want to take that number with the 2 extra digits and put it in here to do the calculation. Some of you are not doing this in your lab calculations. It's not a huge deal, but I'd like you to learn to keep 2 extra digits to avoid rounding errors. Because when I calculate your result, it comes out a little different than yours because of rounding errors. So we're going to put that whole number up there, 0.656, and we're going to include the 47 moles. So we've got 0.65647 divided by 2.50. Our molarity will have 3 significant figures, 26258. And then I round that because this is my final answer, 0.263. Now, how do you express the units here? Well, you can write moles per liter, or you can write capital M. A capital M and a lowercase m, when they're written by hand, can look similar, so I always underline my capital M's to make sure that it doesn't get confused for a meter. Capital M is the abbreviation for moles per liter. Any questions? Molarity is a great conversion factor between moles of solute and liters of solution. When we're doing chemical reactions, a lot of them occur in aqueous solution. So instead of putting a mass of this and a mass of that and mixing these 2 solids together, in which case a lot of times nothing would happen, you have a solution of one and a solution of the other, and you combine the solutions and the reaction takes place in the solution. Liquids are icky to weigh out. It's just not real easy to weigh liquids, but it is easy to measure the volume of a liquid. And so if we know the concentration, the molarity, then we can easily find the moles of the solute using the molarity. So molarity is a great conversion factor. So let's do an example here. Determine how many grams of sucrose are contained in 1.95 liters of 0.781 molar sucrose solution. Well, let's write these numbers down. I have 1.95 liters, and I have 0.781 capital M. Don't write the capital M. Write what it means. Okay? So instead of writing capital M, I know that's what it says there, but capital M is an abbreviation for moles per liter. When you write it out that way, you recognize that could be a conversion factor. If you see just the capital M, you're probably going to be stumped as to what to do. And you don't need to use the equation. Just like with density, you don't need to use the equation to do these problems. So I've got two numbers here. This one's moles per liter. That's my conversion factor. I'm going to start with the 1.95 liters. And then I ask myself, well, what is it asking me to find? How many grams of sucrose? So I'm trying to get to grams of sucrose from this liters. That's the liters of solution. This is moles of sucrose per liter of solution. It can be helpful to spell that out. This molarity allows me to convert from liters of solution to moles of sucrose. Can I get from moles to grams of sucrose? Yeah, I just need the molar mass. 2 arrows, 2 conversion factors. So 1.95 liters of solution times and a fraction times and a fraction. Liters of solution to moles of solution. No, not moles of solution. Moles of sucrose to grams of sucrose. So the moles are down here, those cancel out. And liters of solution is down here, and those cancel out. The first conversion factor is this molarity. This many moles of sucrose per liter of solution. So 0.781 moles of sucrose are in 1 liter of solution. Grams per mole, that's my molar mass, and so we can calculate that. 12 carbons times 12.01 is their mass, plus 22 hydrogens times 1.008, and add 11 oxygens times 16. My calculator is giving me 342.296. We could evaluate, well, how many significant figures are in there? This one has 3, this one has 3, this one has at least 4. We could argue 5, but does it really matter? No, because the number of significant figures in the answer are limited by these 2 numbers, so it should be 3 sig figs. 1.95 times 0.781 times 342.296. So my answer is going to have 3 significant figures. I'm still going to write down 2 extras here and then round this, and it's going to be 522 grams of sugar in this particular solution. Any questions? Yes. Yeah, thank you. Yes, it should be 521. I don't know what I was thinking. And, you know, this is a good reason to write this down, because you can go back and look at it and say, oh, that was dumb. Yes, absolutely, it's supposed to be 521. Thank you. Any other questions? Here's another problem. How many liters of a 0.225 molar KCl solution contains, 55.8 grams of KCl? We can treat all of these problems as unit conversion problems. So 0.225, capital M. That is the abbreviation for moles per liter. Right, moles per liter. And then the other number is 55.8 grams of KCl. This concentration gives us moles of the solute, moles of KCl per liter of solution. So just looking at the units, moles per liters, and just plain old grams, this is the unit we're starting with, and this is our conversion factor. How many liters of solution? So I'm looking for liters of solution. And I have to figure out, how do I get from grams of KCl to liters of solution? Moles in the middle, as often happens. So this molarity would allow me to convert moles of KCl into liters of solution. Liters of solution is what I want over here. So if I got to moles of KCl, then molarity would allow me to do this conversion. Then I have to figure out, how do I get from grams of KCl to moles of KCl? Well, this should be old hat. That's the molar mass, right? So we can convert grams to moles using the molar mass, and then use the molarity to find the volume. So 55.8 grams of KCl, two fractions, because there are two arrows, not two errors. Moles of KCl here, and liters of solution there. There are other ways to solve these problems, and if you're successful with your method, that's great. But if you're struggling and not getting the right answer, years of experience tell me that this is the most straightforward approach. And if you learn this, it'll work all the time. Get all the units in, then I look for numbers. Here, this is moles of KCl per liter of solution. That's what's over here. Now this time, liter of solution is on top and moles of KCl is on bottom. That's okay. 0.225 goes with moles of KCl, so I'm going to write it in the bottom this time. Per how many liters of solution? Per 1 liter of solution. And then here I need a molar mass. So I need the mass of potassium, 1 mole of potassium, 39.1, plus 10, plus chlorine, 35.45. So the molar mass of that one is 74.55 grams per mole. A lot of times when you're calculating a molar mass, you do not get a ridiculous number of digits. Sometimes you'll have a couple extras, but really it's not a whole bunch. And so I tend to just write down all of them. That's at least 4 sig figs. This one's 3, that one's 3. My answer is going to have 3 sig figs then. So 55.8 divided by 74.55 and divided by 0.225. For 3 significant figures, I've got 3.32, and the next 2 digits are 66, and that would be liters. And then when I round that, 3.33 liters of that solution to contain 55 grams. Any questions? So when we're talking about something like sucrose, sugar, C12H22O11, all nonmetals, it's a molecular compound. It does not separate into ions when it dissolves in water. It remains as molecules. So if we say it's 3 molar, that means 3 moles of the molecules. But with an ionic solute like KCl or calcium chloride, when that dissolves into water, it separates into individual ions. And sometimes we are concerned with, well, what is the concentration of a particular ion in that solution? When we report the concentration of an ionic solute, it reflects the concentration of the solute before it dissolves. So if we say we have a 1 molar CaCl2 solution, there's going to be 1 mole of calcium ions per liter but 2 moles of chloride ions. Because in 1 mole of these units, there's 1 mole of calcium and 2 moles of chloride ions. When that dissolves, it separates into ions. We can approximate the concentration of the individual ions from the overall concentration. It's a little bit more complicated than that, but we don't have to worry about it in Chem 1A. So let's determine the molar concentrations of calcium ions and chloride ions in a 0.75 molar CaCl2 solution. So what we're looking for is moles per liter of calcium and moles per liter of chloride. What we've got is moles per liter of calcium chloride. Well, let's write that down. 0.75 moles of calcium chloride per liter. Well, if I want moles of calcium ion per liter, the denominator is staying the same, but the numerator is changing. This is moles of calcium chloride, that's moles of calcium ion. Do we know how many moles of calcium ion are in 1 mole of calcium chloride? Yeah, the formula tells us. So CaCl2. In 1 of these, there's 1 calcium and 2 chlorides. In 1 mole of this, 1 mole of calcium, 2 moles of chloride. So we get this conversion factor from the formula. We want moles of, actually I didn't leave enough room there. Back it up. We want moles of calcium ion in the numerator, and we want moles of calcium chloride in the denominator so that we can cancel that out. And then the units we're left with is moles of calcium ion per liter. This mole-to-mole ratio comes just from the formula. Look at the subscripts. There's 1 calcium. So there's 1 calcium ion for every 1 mole of calcium chloride. So this ends up being the same number. Then let's look at the chloride ions. So again, we've got 0.75 moles of calcium chloride per liter. But we want to find out how many moles of chloride ions are in the solution. So we need to convert moles of this compound to moles of chloride. And when we look at this chemical formula, we have 1 calcium and 2 chlorides. So when this separates, we're going to have 2 moles of chloride for every 1 mole of calcium. And when you do the math there, you get 1.5 moles per liter of the chloride ion. This formula is a little bit like a bicycle, where the calcium is the frame of the bicycle and the chlorides are the wheels. Every bicycle has 2 wheels, right? So if you have 5 bicycles, how many wheels do you have? 10 wheels. How many bicycle frames do you have? 5. Because every frame comes with 2 wheels. In this compound, every calcium ion comes with 2 chloride ions. And when you put those in solution, it's like taking the bicycle apart. They separate. And so the concentrations of the individual ions are not necessarily the same. Any questions?